All right, good afternoon, class. This is lesson, let me double check. This is lesson, hold on, I just lost my, this is lesson 21. This is lesson 21 covering section 5.2 of our textbook. We're wrapping up things with chapter 5. So Monday's lecture covering section 5.3 is really going to be the culmination of everything we're discussing here in chapter 5. But before we talk about 5.3, there's one other phenomenon we need to talk about that happens with eigenvectors and eigenvalues and something called the characteristic equation. This is something that relates to eigenvalues, which is going to have special properties when we look at section 5.3. So let's go ahead and look at 5.2. And as promised from yesterday's lecture, this is a continuation of 5.1 where we're talking about how to find eigenvalues. And part of this we already talked about in yesterday's video, where we have, hold on, sorry, I'm missing my marker. Here we go. Okay. From 5.1, we were talking about how we can find eigenvalues using the determinant. So let me refresh what I was referring to then when we briefly talked about this in yesterday's video. Suppose lambda is an eigenvalue for a square n by n matrix A. Okay, what does this mean? What does it mean to be an eigenvalue? Well, it means there exists a corresponding eigenvector. Then there exists a corresponding eigenvector x, which is not zero. Remember, eigenvectors have to be non-zero vectors, such that times x equals lambda. Definition for eigenvectors and eigenvalues that we have is, well, what if I want to solve for lambda? I want to know what this eigenvalue lambda actually is. I know what is supposed to happen if I have an eigenvalue, but how do I actually find the eigenvalue? Well, the hint that I gave during 5.1 was, well, first, if we subtract everything to the same side, can factor out the x. And notice this is a homogeneous system because it's a matrix equation set equal to 0 with a non-zero solution. Well, because it has a non-zero solution, that means there is a non-trivial solution. And A minus lambda I is a square matrix because A is a square matrix. And we know from the invertible matrix theorem, if you have a non-trivial solution, that means your matrix is linearly dependent. A minus lambda I is linearly dependent. And furthermore, that means the determinant of this matrix equals 0. This is the key takeaway from the section 5.2 lecture here. This is called the characteristic equation, and this is what we can use to find any eigenvalue we could ever want, right? So this is going to be our formal definition. and methodology for finding eigenvalues. All right, so we have definition. A scalar lambda is a eigenvalue, is an eigenvalue for an n by n matrix A if lambda satisfies the characteristic equation. So we're introducing this vocabulary. Characteristic equation. What is the characteristic equation? Well, it's precisely this, where we have the determinant of A minus lambda I set equal to 0. We can use this to solve for any eigenvalues we could possibly like. So let's do an example. Let A be the matrix (2, 3, 3, -6). And we could have a question that says, find the eigenvalues. Okay, how do we do this? I need to look at the characteristic equation and set it equal to 0. All right, so I need A minus lambda I. A minus lambda I, this is the matrix where I subtract lambda down the diagonal. Okay, so now when I take the determinant of this matrix, luckily it's a 2 by 2, so this isn't a difficult determinant to calculate. If it was a 3 by 3 or a 4 by 4 or a 5 by 5, so on and so forth, then you'd have to use those strategies we discussed, I believe it was back in chapter 3, when we talked about how to find determinants. All that stuff we learned in chapter 3, that can help you find the determinant of any square matrix we like. All right, so what's our determinant here? Multiply the diagonal, 2 minus lambda times -6 minus lambda minus 9. Okay, well, in its current state, this doesn't really help me much. I want to know where this equals 0. How do I solve for lambda? Well, first, it might help if we distribute this out and see what happens when we multiply it out. So we're going to have -12 plus 6 lambda minus 2 lambda plus lambda squared. We still have the -9 on the outside. In other words, rewrite the order here. We have lambda squared plus 4 lambda minus 21. This is a quadratic equation, right? I have x squared plus 4 lambda minus 21. Or sorry, lambda squared plus 4 lambda minus 21 equals 0. This is a quadratic, which means I have two options. One, I can factor it, or two, I can use the quadratic formula. So all that stuff you would have learned in college algebra, or a pre-calculus class, or high school algebra. We can solve quadratic equations, right? So that is a prerequisite for this course. It's expected you already know how to solve these. How do we find lambda then? Well, the easiest case here is to factor it. In fact, this is factorable, and we get lambda plus 7 times lambda minus 3. We set it equal to 0, and lambda 1 equals -7. Lambda 2 equals 3. And so we find there are 2 eigenvalues, which makes sense. For a 2 by 2, I could never have more than 2 eigenvalues, because that would then mean that I have more than 2 linearly independent eigenvectors, which could never happen in a two-dimensional space. So this is all of them. These are all the eigenvalues we can find, and I'm using the subscript notation, lambda 1, lambda 2, to indicate which eigenvalue I'm talking about. Okay, so we can now find eigenvalues using this kind of methodology. All right, what else can we do? Well, you also may recall from yesterday's lecture, if the matrix A is triangular, then note that the determinant of a matrix which is triangular is the product of the diagonal. Right? And again, this was something we talked about back in chapter 3. We also discussed it again in yesterday's lecture. So we can use this for supposing you have some larger matrix, which is a 4 by 4, then we can find all of our eigenvalues. Now, the messiness, if we're thinking about the characteristic equation, is that as your matrix increases in size, that means the degree of your characteristic equation is going to go up, right? When I found the determinant for the 2 by 2, I got two linear pieces were being multiplied together, and so I end up with a second degree polynomial. But if A were a 3 by 3, then this characteristic equation could turn out to be a third degree polynomial. In fact, when A is any n by n matrix, its characteristic equation is going to be an n degree polynomial. So for larger size matrices, it can be more difficult to find the eigenvalues when the matrix is bigger, because then the polynomial gets bigger. So using this characteristic equation methodology is not always the best way to go about it. However, if we first simplify the matrix by row reducing, then that might give us an easier way of finding the determinant, and so give us an easier way of finding the eigenvalues. For example, suppose the matrix A is given here, where A equals 5, -2, 6, -1, 0, 3, -8, 0, 0, 0, 5, 4, and 0, 0, 0, 1. Now, lucky for us, this matrix is triangular. And we also know from section 5.1, when your matrix is triangular, your eigenvalues are the diagonal entries. So we automatically know that I have eigenvalues which are 5, 3, or 1. But notice that 5 is repeated twice. Well, what does that mean? Well, if instead we think about using the characteristic equation methodology, then we're going to see, okay, well, A minus lambda I equals 5 minus lambda, -2, 6, -1, 0, 3 minus lambda, -8, 0, 0, 0, 5 minus lambda, 4, 0, 0, 0, 1 minus lambda. Again, this is still triangular, so when I take the determinant of this matrix, it is the product of the diagonal, and we have 5 minus lambda times 3 minus lambda times 5 minus lambda times 1 minus lambda. Or in other words, I could rewrite this as 5 minus lambda squared times 3 minus lambda times 1 minus lambda. In other words, the number of times your eigenvalue appears is telling you the multiplicity of its factors in the polynomial for the determinant here, right? So if you remember from college algebra, multiplicity is referring to how many times a root for a polynomial appears. In other words, what is a root? This is when you plug in something and you get a 0 for your polynomial. The root for 5 appears twice in the polynomial. It has multiplicity of 2. Why do we care about multiplicity? Well, multiplicity can also be determining how large an eigenspace is, right? The multiplicity is also going to tell us the eigenspace that goes with the eigenvalue of 5, maybe that eigenspace is two-dimensional. Whereas the eigenspaces that go with lambda 3 and lambda 1, they are restricted to being one-dimensional because their multiplicities are 1. So this multiplicity business can also help indicate how large a given eigenspace can be. Now, this is something we're going to go into more detail in 5.3 in Monday's lecture, but I want to go ahead and start talking about multiplicities so you can start recognizing the multiplicity because this is going to be important later. All right. So before I erase this, or at least I'm going to erase part of it, I do want to, in case you don't remember, I want to highlight the definition for multiplicity. Right? So definition. The number of times an eigenvalue appears in its characteristic equation which is precisely what this is right here. This was the characteristic equation that we calculated. The number of times an eigenvalue appears in its characteristic equation is its multiplicity. Right? So in this example, lambda 1 equal to 5 has multiplicity, and I'll abbreviate here, has multiplicity of 2. Lambda 2 equal to 3 has multiplicity 1. And lambda 3, which equals 1, also has multiplicity of 1. Now, some special things to note about this multiplicity. This was for a matrix A, which was a 4 by 4. Because it was a 4 by 4, its characteristic equation turned out to be, this is a 4th degree polynomial. If you multiply all of this out, you're going to have lambda to the 4th power time plus some other stuff, right? So this is a 4th degree polynomial, but we can also see here that the multiplicities add up to the total degree of the polynomial. This is a 4th degree. And we can see here that 2 plus 1 plus 1 equals 4. And in fact, this is no coincidence. This is always going to happen. Your multiplicities are going to add up to the degree of the matrix. Okay, great. Now, one of the last pieces I really want to highlight for two matrices to be similar. Now, this vocabulary term, it's kind of an oddball term that doesn't actually appear very often in linear algebra. However, it is going to be crucial for understanding some definitions that we're going to cover in 5.3. So while the idea of two matrices being similar really isn't that important, it is going to be a building block to get us to the big deal theorem stuff that we're going to talk about in Monday's lecture in section 5.3. Okay, so what does this mean? What does it mean for two matrices to be similar? So let A and B be n by n matrices. So first of all, they're both square, but they're also the same size. They're both n by n. They're both 2 by 2s, or they're both 3 by 3s, whatever it is. They're both the same size. Then we say A is similar to B if there exists an invertible matrix, capital P, such that P inverse times A, so P inverse exists because P is invertible. P inverse times A times P equals P, B, P inverse. In order for A to be similar to B, we're saying that there is some way to sandwich the matrix B with an invertible matrix and its inverse on the other side, and somehow these two things are equal. This is also referred to as a similarity transformation, but it's also noteworthy that if A is similar to B, then B is also similar to A. This relationship goes both directions. Why? Well, if A is similar to B, then I can just multiply the P stuff over to the other side, and then I'll have that B equals a sandwich of A, right? So A similar to B implies B is similar to A. It goes both directions. If A is similar to B, then B is similar to A. Now, as far as like how do we determine if two matrices are similar, or rather, how do we find similar matrices? This is what we're going to do in 5.3. However, for today, I just want to introduce this term, get us kind of used to it, and I want to go ahead and give an example of two matrices that are similar so that we can see why they're similar. All right. So let's take a look at this example. And remember this equation here. A equals P, B, P inverse. All right. So here's an example. Let A equal the matrix 1, 2, 3, 4. Going to keep it simple. And let's say B is the matrix 2, 8, 1, 3. Okay. Now my claim is that A is similar to B. Why or how? Well, A is similar to B with matrix P equals 1, 3, 2, 7. All right. But where is this matrix P coming from? How do we know how to find matrix P? How do we know matrix P exists? How do we create matrix P? These are all questions we're going to discuss more so in 5.3. Part of the hint I'll go ahead and tell you is that this has a relationship with eigenvalues and eigenvectors. All right. But first of all, in order to be similar, P has to be invertible. Well, is that true? The determinant of P is equal to 7 minus 6, which equals 1. That is not 0, so great. P is invertible. Okay, so that's good news. In fact, we can find P inverse. P inverse equals, swap the diagonal, put a negative on the off diagonal. Okay, great. So now, if A and B truly are similar, this means that A equals P times B times P inverse. Okay? So we can check this. Here I have P is 1, 3, 2, 7 times B, which is 2, 8, 1, 3 times P inverse, which is 7, negative 3, negative 2, 1. So we can carefully check this matrix multiplication. I'll just do this matrix times this matrix first. We can use the dot product, and we're going to get 2 plus 3 is 5. 8 plus 9 is 17. 4 plus 7 is 11. 16 plus 21. What is that? 37? Okay, so the numbers got kind of nasty here. But the claim is that if I multiply this with 7, negative 3, negative 2, 1, I'm supposed to get 1, 2, 3, 4. All right. Well, 5 times 7 will result in 35. Minus 2 times 17 is going to be 34. 35 minus 34 is 1. Okay, so far so good. 5 times negative 3 is a negative 15. Plus 17 times 1 is 17. 17 minus 15, we get 2. Okay, that's good. 11 times 7 is 77. Minus 2 times 37 is going to be, what is that, 74? So we get 3. That's good. And then lastly, negative 33 plus 37 gives us a positive 4. So lo and behold, this matrix A and this matrix B are similar. And they are similar when we use the invertible matrix P, which is 1, 3, 2, and 7. Okay? How do we find, if I just give you a matrix A, how do we find a matrix B that does this? And then also, how do we find a matrix P which does this? Those are all details we're going to discuss more in 5.3. But I just want to go ahead and introduce these ideas so we get used to them. And then we're going to talk about them more in the 5.3 lecture. All right. Let's see. So we may end a little bit earlier. The last point I want to highlight here before we do today's participation question. We know these two matrices are similar. However, what else is special about them? Well, if we think about what about their characteristic equations, since that's what we were at first studying for 5.2, what happens with their characteristic equations? Well, we can see here the characteristic equation for A is the determinant of A minus lambda I. Okay, what is that? Well, I would subtract lambda from the diagonal and multiply. So I would have 1 minus lambda times 4 minus lambda minus 6. If we simplify this, we're going to get 4 minus 4 lambda minus lambda plus lambda squared minus 6. We have lambda squared minus 5 lambda minus 2. All right, this is the characteristic equation for A. What about B? The determinant of B minus lambda I, and my blue marker is dying on me. Let me switch to a different marker. Well, I'm going to subtract lambda down the diagonal and then take my determinant. So I have 2 minus lambda times 3 minus lambda minus 8. What do we get here? Well, we're going to have 6 minus 2 lambda minus 3 lambda plus lambda squared minus 8. We have lambda squared minus 5 lambda minus 2. Lo and behold, these two matrices have the exact same characteristic equation. Not only do they have the same characteristic equation, but this means they have the same eigenvalues. They have the same eigenvectors. So there's actually something special about two matrices being similar, in that this is going to automatically tell us that they also have the same characteristic equations, they have the same eigenvalues, and therefore they have the same eigenvectors. All right. All of this we're going to explore in greater detail when we look at 5.3. And we're going to see how else we can use this property of similarity between matrices. All right. With that being said, let's look at today's participation question. This is participation day 20. I'll go ahead and share my screen. Participation day 20. So we're given the question here. If an n by n matrix A has an eigenvalue of 0, then does A correspond with a one-to-one transformation? What about an onto transformation? Okay, what does this mean? So we've talked about, or we've seen examples of having different cases of eigenvalues or eigenvalues that repeat. But what about when we have an eigenvalue of 0? What does that mean? Well, you can imagine, as in like a 2x2 matrix, we know that when we have a diagonal matrix, then the eigenvalues are the diagonal entries. Well, imagine if you have a 2x2 matrix and there's a 0. So let me see, I can mirror the screen here. You can imagine with me, then what if, so this is for the participation question, I give you a matrix which is like A, B, 0, 0. Doesn't matter what A and B are. This is a triangular matrix, and it has an eigenvalue of A, and it has an eigenvalue of 0. But what else is true about this matrix? Because I have an eigenvalue of 0, that means I'm missing a pivot for that column where I have an eigenvalue of 0. And if I'm missing a pivot, that means this matrix is linearly dependent. Okay, so now let's go back to the question. The matrix A is linearly dependent because we have an eigenvalue of 0. So does A correspond with a one-to-one transformation? What about an onto transformation? Think back to the invertible matrix theorem. For square matrices, one-to-one and onto are equivalent to one another. But if I'm linearly dependent, that means I'm missing a pivot. I am not one-to-one, and therefore we are also not onto. So in fact, that's going to give us our answer for today. A does not correspond with a one-to-one transformation or an onto transformation. It can't be either one of them because there's not enough pivots. So that's it for today. That's going to be answering our participation question. If you have other questions, by all means, please do email me. We can talk about it. Otherwise, that's all for today. Office hours will continue next week. So next week we do have our final exam, which means if you've looked at the schedule on Canvas, you'll see that on Tuesday we have a scheduled review session or planned review session. So instead of an office hour on Tuesday, we're going to do a review session for the final exam, and we'll prepare for the final exam to be on Wednesday. The final exam is going to be very similar to what we did for the midterm, kind of a timed situation. You'll have 2.5 hours, and same as before, you'll have access to it, and then you'll have to complete it within that time frame and then upload it to Canvas, just as you did for the midterm, right? Those questions will be similar to like the homework problems, so you can use that for practice. I can also publish a set of other suggested exercises that you can use for more practice. So remember when I published those exercises for the midterm, those were the odd questions. And the odd questions in the textbook have their answer in the back. So you can use that to study and prepare. And hopefully you'll be in a good place for the final. All right, that's all for today. Best of luck. I will see you next week.